Hi all. First of all, thank you so much for coming on this Thursday evening to our office. I mean, we believe these meetups are a good way for us to meet new people. And may you be like a professional or a student, I believe you can take something out of it. Yeah, as I mentioned, there are food and beverages are on the side. Please help yourself. Yes, and we are DK or Decathlon, and I am Varun. I'm one of the machine learning engineers at Jago or DK. And yeah, so what is DK? We are basically the engineering arm of Bank Jago. Jago is one of the leading digital banks in Indonesia, and yeah, we basically offer us. We are another big go-to umbrella. Where exactly is another meetup topic itself. Uh, so yeah, we have our offices all across Pune, Jakarta, and Singapore. Yeah, we have the work from anywhere policy, and talking about jobs, we would be really great to let you know that we are hiring, and if any one of you find anything interesting, please hit us up. At the same time, this ML meetup is open to everyone. We would be more than happy to have your submission. We'll arrange the food and everything in this area. It'd be great to have you present us here for any of the topics. And yes, we do also have stickers on the site. Please help yourself to those stickers. Yeah, I mean, that's it from my commercial perspective. Let's start with the main show. Yeah, which is today we are having Steph to talk about credit risk modeling. Steph is one of the senior data scientists at DK, and she has worked previously as an analyst and for multiple various banks in across APAC and America. Uh, yeah, and she's really awesome, right? And uh, apart from that, she has also been head of credit risk in a bank, one of the major banks of Philippines. Yeah, Steph, I mean, it'd be great for you to just let us know more.
Oh, hi everyone. Okay, wait. Aha. Okay, so thanks everyone for joining both online and here in our wonderful office. Okay, so yeah, again, I'm Steph and I'll be leading this discussion. So today it's an introduction to credit risk modeling. So I know that we have quite a wide audience. So some of you may have banking experience, some of you may not. So I'll try to make it palatable for everyone. Okay. So obviously this is our agenda. Talk about credit risk, and it also go through some of the major components, such as how do you do the model design, what are some of the things we do for feature engineering selection, what are some performance metrics we look at, what is score calibration and lastly scaling, and what are some strategies we can do using score bands. Okay, cool. So first off, what is credit risk? So here you can see behind me is basically the credit risk models across the customer life cycle. Okay, so you can see the horizontal axis that will be the different stages or as you go through the journey of a customer. And then on the y-axis, you have what is called the customer value. What you can see, what you already observed here is that there is a fluctuation, obviously, depending on where you are in the customer life cycle. So let's go into it. There are four major segments, as you can see, in the life cycle. You have prospecting, acquisition or origination, customer management, and collections or asset recovery. Now, the gray line there that you can see, is we can think of it as like a zero, right? Uh, Zero customer value. What does that mean? So when the line, the magenta line is below that gray line there, that means that usually we invest more. So there's an outflow contributing to lower customer value. And then once there is a take up of the account, then your customer value starts to increase. So at the very beginning, like here, prospecting, what you want to do is to approach or look for new customers. So you offer products and services. So you spend more. Therefore, there's an outflow, right? And here you have what is called, you can use propensity models to target the right offers or products to your prospective customers. And the main objective is that it can help improve your customer loyalty or reduce attrition rate if your propensity models are okay. But this is not necessarily a credit risk model. So that's why when you look at the gray box below under CR models, you don't see it here because that is a propensity model. But once that account goes into your books, right? So that borrower is already part of your portfolio, then that is part of your acquisition or origination. So that borrower has started the journey in the books, right? So at this stage, this is when a prospective customer approaches the bank and we start the application process. So we have what is called the underwriting process. Basically, it's an assessment of the customer's ability to bear their future debt obligations. And here below, you can see what is the appropriate credit risk model that you can use. It's an application or your scorecard, which basically helps in risk profiling, and the objective is to decrease your bad customer acquisition. Okay, clear so far, right? It's pretty easy. So next is we try to go to customer management. So here, the objective is to continue to increase your customer value. And here, so if previously, right, our goal was to optimize the entry of good customers. In customer management, what you want is to keep the good ones within your organization. All right. So how do we do that? If you look down at the CR models, you have what is called the behavioral scorecard. Okay. And so behavioral scorecards are usually used to risk rank also your existing customers. And then for the good customers, what you can do is you can do upselling or cross-selling, which means you, for example, if it's a credit card, you can increase the limit. So that is an upselling. If it's cross-selling, if it's an existing credit card customer, then you can offer, okay, how about a home loan? How about an auto loan? So this is one of the uses of having a behavioral scorecard. Okay, then obviously, as the customer progresses, he or she can either be a good account or a bad account, right? So there, if it's a good account, then the loan approaches the end of the tenor, and then it exits the entire journey through an account closure. So the loan is paid off basically. But in certain circumstances, we also have a bad account wherein there's performance deterioration, and this is when you see the borrower start not paying installments, and then uh, starting to default, right? And so you have what is called collections or asset recovery part. Before you even go there, you try to win them back. And this is what the early warning model aims to do, right? It signals early deterioration so that you can catch it easily, and then you bring back or win back that customer. But in case that customer still proceeds to, being in default, then you have what is called a collection scorecard. The purpose of a collection scorecard is to streamline your collection tasks. So usually there are different wristbands also, and per wristband you can offer different types of strategies for collecting. Okay, and so this one, the application scorecard, behavioral scorecard, and the collection scorecard. These are like the very basic models that you use for credit risk, and they are also known as the ABC models. But below that, you can see that we also have what are called the regulatory models, and these are based on IFRS 9 or Basel II standards. You have the following: probability of default, loss given default, exposure at default, and you also have this thing called the significant increase in credit risk. Right. So we won't really talk much about the last part, the regulatory models, because that is honestly a whole new section altogether. But you can leverage you can uh, develop the PD models by leveraging your ABC scorecards or ABC models. Okay, clear so far? All right. Okay, next up is your 5 C's of credit. So why am I even talking about this? Um, first, because it helps us understand what features we can look at and we can use for model development. Okay, so also, by the way, if you don't have sufficient data, because when we do model development, obviously we want like thousands of observations, right? But that is not always the case. So if you don't have sufficient data, banks may still employ what is known as judgmental scorecard. But basically, it's like a manual scorecard wherein it's just on a score point basis, and it's based on usually just the credit expertise of the team, right? Okay, let's go through it. So the 5 C's are capacity, character, capital, collateral, condition. Okay, so what is capacity? Um, yeah, basically ability to repay the loan. What can you look at for this? You can check for the demographics such as monthly income, debt to income ratio, expenses. And if you're looking at corporates or companies, then you can take a look at the financials or business revenue, for example. Now let's go to the next part, character. It says borrower's reputation or track record for repaying debts. Okay, so this basically means like credit history, right? So basically bureau information. And also if they are like part of a blacklist of non-payers. And usually you can see this in news, right? When a company like goes bankrupt. Um, Next one is capital. So this could be like savings accounts, other investments. If you're looking at corporates, then this can include like personal investments of that person into the firm. You can also take a look at retained earnings and other assets. So the basic idea for this one is to look at supplements that can repay debt obligations if there is an issue with the borrower's major source of income. Okay, collateral is kind of self-explanatory. This is an asset that backs the loan or can be seized or captured by the bank in an event of default. And lastly, you have condition. Okay, so this can be external factors actually that can contribute to the borrower's ability to repay. So you can include macroeconomic factors, but usually macroeconomic factors are used for IFRS 9 models. Um, you can use instead like a proxy to the economy by looking at business type or economic sector or industry type, for example. Yeah, that's it pretty much. Okay, so now let's go to the model development part. Right. So this would be the scope of the presentation. So it will focus primarily on like typical modeling approaches, right? It's a good bad classification basically. And then we'll be focusing on binary classification. So I just mentioned good bad, right? In other cases, you might have multi-class problems wherein you can have good, bad, and also indeterminate. But for this presentation, we'll be focusing on just good bad classification. Okay, and then sorry for those using R or SAS. I won't have examples here. Is anyone actually using SAS? Okay, we're using Python now. And then lastly, yeah. So as mentioned, it can be used. This approach can be used for ABC models, right? And maybe even for PD. All right. And okay, I'll just be brushing on some concepts basically. since this is an intro. But if there are topics you feel should be covered in more depth, just approach us. Okay. Right. So let's start with the model design. So there's this concept called windows. When you're first developing the model, consider what is the objective or purpose why you are doing it, because that will dictate how you will do the model design. Let's talk about the concept of windows. Okay, so in general, you can divide the periods that you have into two main windows we call the observation and the performance window. Okay, so here you can see M0. Okay, I think let me just, oh, it's not working. Aha, right. Okay, so this M0 means month 0, and then you have L1M until last X months. So basically, this is last 1 month, last 2 months, etc. And then from here, you have month 1 month after M0, and so on and so forth. Okay, easy so far. Okay, let's talk about this. So this M0 here is called the observation point. So you can think of this as like your reference when you're trying to divide your past data and your future data. So your past data is where you will get all your features or all your historical information. Okay, and then your future information will be your performance window. For A score, what is our observation point? So obviously that will be your application month for A score. But for B and C scores, behavioral connection, okay, that will be the reporting month. Okay, and then this one, so I mentioned already, this is the observation window. This is the period where you will generate characteristics. And then lastly, this is the performance window where you will define your target. Okay, watch out. There's this thing called data leakage. Okay. And this can be really bad. So sometimes you may get a performance that's really good. So for example, I had this, the performance was like 0.8 AUC, originally from 0.7. So you might think that this is a huge improvement in your model, but actually, you have to check again because maybe the performance may seem too good to be true. So, what do you do to avoid data leakage? First is to ask yourself, have you included information not available at observation point? So what does it mean? So at M0, right? Let's say you are developing an application scorecard or an A score. So at observation point, you might get bureau information as of that month. But in actual reality, banks only provide information from last month. Okay, so is it clear? So every month, the bank, for example, this month is February, the banks may only provide information from January, right? Or before that. So when you're doing the application scorecard, remove information which are actually not available. Do you get that? Do you get what I'm saying? Okay, cool. And then lastly is to see if you've used test or OOT data for training. So more on this in the next slides. Okay, next is the target definition. So we have what is called the roll rate analysis. I guess is everyone familiar with roll rate analysis here? Have you heard of it? Okay. So basically, you can think of it as a transition matrix. Okay. Okay. Right. So think of it as a transition matrix where you have a start month. And then you take a look at how much of the start accounts moved to a different bucket after a certain period. So this is an example here after 3 months, right? You start with, let's say, current, and then you have 1 to 29 days past due. I hope everyone's familiar with the concept of a days past due. If not, let me know. Okay, then you have 30 to 59 days past due, 60 to 89, 90 plus DPD, right? And then after 3 months, how much of your current accounts still remained as current? How many worsened to 1 to 29, 30 to 59, and so on and so forth. So you do the same for all buckets, and then you compute how many rolled back and how many rolled forward. So basically, it's just the sum of those accounts that move to the worst buckets. So in this case, the ones that rolled forward for current accounts are 13%, which is 9 plus 3 plus 1. That's this one. And then for 1 to 29 is this plus this plus this. Oops. All right. So why are we doing this? Because we want to see how many actually moved, where the percentage moved to the worst bucket. And which bucket shows the worst performance in terms of how many rolled forward. Because if you use 1 to 29 DPD, then actually a lot of them went back to current performance, right? So here you can choose to use the 30 to 59 BPD as your target, right? Or the Y of your model. Okay, so this one looks simple, but if you want more in-depth analysis, then you can look for other periods and of course check for the binning or the bucket of this one. Okay, now let's assume that the chosen performance window is 3 months. So we'll talk about more how you can choose the length of your performance window. But let's assume that the chosen performance window is 3 months. Then how will you define your good or bad? Right? So let's give some examples here. Okay, so you recall what month 0, month 1 are, right? If you go back here, it's basically this part. Right. Okay. So for each account, you can take a look um, at the performance of each month in the performance window, basically. Okay, at month 0, you expect that all of them will be in current status or good status. And then if not, then I suggest you drop that observation. That is called a non-starter, and that can affect your model development. Okay. Here we can tag a bad account if it exhibited a bad performance in at least 1 month in the performance window. It's good if everything is 0, obviously. And then should we include or should not include those with incomplete performance windows? So that is a question here. And we remember the concept of censoring. In this case, let's say this account with performing well in the first 2 months, but in the 3rd month, it's incomplete. So, right, let's say that this last December, and then in January, it's still performing well. February, which is this month, is performing well. March, we don't know whether it's performing well or not. In this case, this is unknown, so we drop it. But in the last example here, we already know that in February, this observation is not performing well. So we call it as a bad guy. So we can include this in the model performance. All right, so just be aware though, when doing this, because you might not have remaining observations for your OOT, or your OOT data might be tainted as well, because you're using it for your training. Okay, so I hope that is clear. All right, so this is one way of doing it. Here is another way of doing it. So this one's more conservative, right? But here, let's say you want to define your bad as 2 consecutive bad performances instead. So in this case, this will be bad, and then this will still be considered good. Okay, So what is actually bad? I've been saying 1 or 0, right? What is bad? So it can be based on the days past due, which we've defined here with our roll rate analysis, but still depends on, and it still depends on the objective of your model, right? So we can use the roll rate analysis to assess whether we're going for a 30 DPT or not, or if it's something regulatory, then they might say, let's use a 90 DPT. Okay, so just take note of that. And it may also include accounts that are under litigation, those that have are bankrupt or planned for AR transfer. And 0, obviously, is the opposite of the what's about. Okay, are you guys still okay? Okay, no questions? Right. How about those online? Are you still okay? Okay, nice. So let's go to the next part, which is choosing the performance window. Okay, so this one is called vintage analysis. Basically, you plot your booking month, where your 0 is the okay. So let's put it this way. So you plot each vintage where your axis is the MLP. I think there's a question. Okay. All right. So this is basically plotting your different application ones into your MOP and then checking at which point are there peaks in your ODR. So the y-axis here is your observed default rate. So basically, this is what we've defined as bad in the previous exercise, right? And then we're just checking at which point are there peaks in your ODR. Okay, so the common options for performance window will be, in this case, will take 6 months. Because here you're seeing peaks here, and then afterwards it just drops. Okay. So how do you actually decide? So here are some considerations. First, is a covered time period enough to ensure accounts are mature? So let's say you want 3 months instead, then you might not capture sharp peaks in bads in latter periods. So you aren't able to capture this. If it's too long, however, let's say it's 18 months, not included here, then there will be trade-off in model monitoring. So if it's 18 months, then you need to wait for 18 more months to see the full performance of that cohort. Okay. Then next part is, if do you have enough goods or bads to do model development? So this here, right? The definition of is it enough would obviously depend on also like it's a function also of how many features you have in the model. But hopefully we're getting like maybe at least 1,000 for model development. Okay, and then last one is if your model is affected by a regulatory standard. Okay, so even let's say you've done the vintage analysis, but if you're doing this for IFRS 9, then the performance window is actually 12 months. So you need to take that into consideration. Okay. Okay, so this one is pretty standard. It's called the data splits, and you can use it for other model development exercises. It's basically just dividing our data sets into subsamples of your in-sample and out-of-time sample. And from the in-sample data, of course, you need to divide it into your train or test. And this will depend on data availability. Okay, so for credit risk, usually we would want to have 2 to 5 years worth of data. But obviously, this is not always the case, and it can actually be quite time consuming. So take that into consideration. Okay, next. So class imbalance. Okay, so why do we do it? So class imbalance, by the way, is when you have, obviously you have majority class and then what you call the minority class. If your minority class is very small, so in this case, your majority class is your good accounts, right? Then your minority class will be your bad accounts, hopefully. Otherwise, why are we still lending? Okay. So why do we do it actually? So models are trained obviously on your available data. So if there is significantly more of one class, then the model may give you high accuracy, but it is actually bad at classifying the minority class. And this is really important to, to be able to predict your minority class. And this is so much more important in fraud, actually, if anyone has worked with fraud models before. Okay. So there are several ways of going around it. So what can be done? First is very obvious. Check for more data. And then the second one is to use a different performance metric. So I mentioned accuracy before. You can actually use other performance metrics where this is not the main focus. And then you can also try tree-based algorithms so it can better handle class imbalance. And lastly, you have some sampling techniques below. Okay, so obviously you have undersampling and oversampling. So undersampling from our image here basically is you you sample the majority class, but only a certain portion so that it can be almost the same as your minority class. So you can do this by random sampling with the replacement of the majority class. There's what we call the connect links. It's just basically removing pairs of instances but of opposite classes. The way to do this is that it kind of increases the divergence between your minority and majority class. And then you can also try clustering prior to random sampling. The pros of this obviously is that the training data set is large, then it will help reduce runtime. But the disadvantage is that you're potentially removing useful information and you might be sampling from an incomplete subset. So that means that you might be getting a subset which is not representative of your population actually. Then the next one is called oversampling. So again, if you look at the image here, so you're getting basically copies of the minority class. You're trying to amplify or augment the minority class. And you can do it random sampling with replacement of minority class, or you can also try smooth. So the good thing about this is that you're not losing information and that it will more likely outperform undersampling. Unfortunately, this may be prone to overfitting, but you can work on that a bit more later on. Okay, are there questions so far? Okay. Okay, data preparation. So here are some ways where you can handle missing data. So from here on out, it seems like it is mostly same with other model development, right? So for data preparation, you can, for missing data, you can do imputation, but make sure that the values are missing completely at random. So what does that mean? Basically, the missingness cannot be observed by other features or events. Basically, it's random. It's just missing at random. So an example of this is like when you get data entries that are missing. Okay, so that's an example. What is not random, for example, is if you have bureau tagging. So let's say that your bureau tagging flags whether there is bureau information or not. So obviously, if there's no bureau information, then you will have a lot of missing information coming from bureau. Okay. And then usually you do imputation when your missing values only comprise like a small percentage of your total population, let's say 5%. Um, and you can impute using mean if it's normally distributed, and for continuous numerical values, or median if the variable is skewed, or if you expect a round number. Okay, so these are some examples. And then what else? So you can also treat it as a separate value. And this is when the missing values are actually not missing at random. In this case, I was talking about the bureau tagging, right? So if there is really no bureau observation, I can actually just leave it as is, and then it's a separate category on its own. So in this case, you can just put fill in a missing. Okay, and then the last part, the last way you can handle missing values is through exclusion. So you can exclude it by rows or by columns. Yeah, and for outliers, it first, how do you detect outliers? Well, you can use business expectations usually. Like, what does a business expect? Do we expect it to have negative values? Do we expect the income to be at this limit, or to be 10 million, for example? Or you can also just use calculations here, such as using the IQR or some percentage. Okay, so we can use that. And then for treatment, how do you treat outliers? So you can do capping or flooring. So basically just set a minimum value and or maximum value. You can exclude it or you can leave it as is. So for this one, again, it takes a bit of consideration also. If the feature values are natural or expected, then maybe it's best to leave it as is, because you're also missing an information there. Okay, another reminder to not forget about issues on data leakage. So what does that mean? You can do this preparation, like for example, calculating your, doing your imputation, or doing the treatment on capping and flooring on the trained data set. Okay, separate it from your test data set. Okay, cool. And then next one is called row-wise exclusions. Okay, so before you move to feature engineering and selection, consider some cases where you want to exclude observations in the dataset. Why do you want to do that, actually? Because you might be removing information, right? So why? Any guesses? Okay. So here are some examples of what we want to remove in our accounts, right? You have special accounts like VIPs, employee accounts, or accounts under moratorium. If you recall, when we had COVID, the pandemic, there are accounts who went under moratorium. And then, for example, there are time periods affected by temporary events, right? Or events that are likely to discontinue. Then you also have deviations in your credit policy. You use mock accounts, or there are just simply erroneous accounts. There are borrowers who have passed on, and what I mentioned earlier, non-starters, and sometimes fraudulent accounts. So why do we want to actually remove them? Any guesses? Okay, so basically you want to remove them because they are treated in a different way, different manner. So if you're doing like an A score, right, you will go through the same process as everyone else. That's expected. But at times, like for example, the first one, the VIP account will have a separate processing. Or if you're an employee account, then definitely you will have a different application process. So we remove all of these because that may contaminate your population. Yes. Uh-huh. Okay. Yes. So fraudulent. Okay. Actually, fraud model on its own, separate from credit risk. That's why we also want to just remove it here. Because fraudulent accounts, right? They will give you such a good picture of themselves usually. That is a different modeling thing. Yeah. Yeah, we should apply. Correct. Good question. Thank you. Anyone else? Okay, cool. Feature engineering. Okay, right. So these are basically different types of data that you can look at. And over here are the possible or the typical models that you can use this on. Okay, data type. Demographics, obviously, the profile of borrower. Bureau, coming from bureau information. I hope everyone's familiar with what the bureau does. If not, just let me know. Okay. So basically, bureau would have your historical credit history, basically. And then for transactional, that would be, um, for example, payments over time, total exposure, assignment balance, how you use your limit, uh, and then do you have existing deposits. Click string is the interactions in the app. If you have an app, basically like for the bank, if you have an app, then you can see like the interactions, and the types of interactions also. For collateral, self-explanatory, basically, what is the collateral value? Is it a house? Is it a car? How much is covered? How much of the debt is covered by collateral? Then you have collections. Collections basically is like collection activities, right? SMS, uh, how many SMS were sent so that you can collect? Or did you make calls? Did the borrower make promises? How many were broken? So sad. And then you have telco information, right? So basically, yeah, uh, top up amounts, number of calls made. You have partner data, uh, which is helpful if, like Jago, you have a lot of partners. We're dealing with a lot of partners. So, and then lastly is external public data. And you can use this to do affluence estimation, maybe based on location, land price, property price, all of that. Okay, right. So let's go to the next part. Okay, right. So these are just some examples of how you deal with numerical features. So as mentioned, right, for generating features, you do it in the observation window. And here are some examples for numerical features. One, ratios. This is usually, well, obviously, when it's just a nominal amount, it may not really tell you the true profile, or the true capacity to pay of a borrower, in which case you convert them to ratios. Let's say, for example, income. A person may have really big income, but if that same person has a huge amount of debt, then if you compute the debt to income ratio, then that ratio may not may be actually better compared to just looking at the income of that person. Second one is recency, so how long since an event has happened. Uh, the third is frequency or count, uh, just basically counting uh, of an event. So, for example, you paid off a facility, how many times or how many facilities have been paid off in the past. Then you have transformations, which I don't normally do, but that's basically because I don't use it for the models. They are not required by my models. But if you're exploring neural nets, for example, then it's best to do something like this. Okay, then you have aggregations. So I put here minimum, maximum, average, and experience. You can also include median, if that is more appropriate. Okay. Okay, so one thing about this one, uh, on the aggregation logic, is that you can definitely apply it on all of your features, but make sure that it makes sense as well. So one example is, let's consider that a borrower has 3 facilities with varying tenor. So if you sum up the tenor, for example, 1 month, and then you have another with 24 years and another one with 12 months, if you sum them up, it really does not make sense. And it won't help how you explain the model. Okay, so just take that into consideration. Then the last one is called classing or binning, and I'll discuss that separately. Okay. All right. So categorical features. Okay. So we have what is called encoding without the target. So basically, it's just you can think of it as mapping a number to a specific categorical value. So for example, label encoding, let's say that you're here to tag whether the borrower has a property, has a house, for example, then the answer is yes or no. Then it's basically just mapping it as either one or zero, something like that. For ordinal encoding, so it's kind of similar, but here order matters. For example, you have the following: very hot, hot, lukewarm, cold, very cold, and just put 1, 2, 3, 4, 5. Okay. Then you have dummy encoding and one hot encoding, which is easier explained through this. So you can transform from label, make it into a dummy encoding, which is basically just n-1. Then you have one hot encoding, which is just a bunch of ones and zeros for all of the labels here. So four labels for four flags for one hot encoding, but three for dummy encoding. So just watch out for what is called the dummy variable trap. This is basically like multicollinearity, basically, because here one hot encoding, you're putting ones and zeros to all flags. Um, and if you look at, for example, fall flag, and there's no added value to it. It's like the other three flags are able to capture the data that you need already. Not sure if I explained it properly, but basically, just avoid um, um, just avoid putting flags on all of your labels because that will result in multicollinearity. Okay. And then there's another one, which is encoding, but this time it's with the target variable. So there's what we call the weight of evidence encoding. Basically, it's just calculating your WOE per category, which is the log of your of the distribution of goods over the distribution of bads. And then for target encoding, this is just the average of the targets. Okay, better explained with this one. So let's say the marital status, you have married, single, divorced, and others. So to compute for your WOE encoding, it will basically be just the ln of your uh, percentage good divided by the ln of divided by the percentage of bad. Whereas target encoding is just basically the bad rate, so bads over goods, bads over the total per bin. Okay, so what do you observe here? For WOE encoding, right? If it's negative, then you can see that the percentage of good is less than the percentage of bad. So this is one of the reasons why, for conventional approaches, people lean towards using a WOE encoder instead of a target encoder. Okay, but doesn't mean that one is better than the other. So I would actually encourage you to explore what would work best for your organization. Okay, now we go to what is called the classing, well-defined and coarse classing. You can just think of it as another term for binning. And what do we want? So we want to have monotonicity, and we also want to have sufficient population per band. So this is very important if you want your features to align with certain expectations by the business, which is an interesting point there. So what do we want? So this is your fine class. You have several bins actually. Then what you would want is just to combine them so that at the end of the day, you are left with something like this. This is called coarse classing. So what else is here? is that the percentage of population per band should be at least 5%, and then your band rate would be monotonic. Okay, and here are some things to consider. So if there's no clear trend, right, just looks flat, meaning your band rate is just flat like that, then you can consider to filter this out of your features. Um, and then next one is on predictive power. So based on this bin that you have, you also compute for what is known as the information value. And if the feature has a low information value, then you drop it. So I'll discuss a bit more on this in the next few slides. Okay, so something here to consider also is just because it doesn't match certain business expectations, it doesn't mean that you have to drop it. So this needs to go through several discussions also with the team involved. Um, so just think about what would be the best solution for the team. Because if you don't have a lot of features, then even those with counterintuitive trends might be helpful to include them still. Okay. Okay, so this one, right. So yes, do you have a question? Okay. So yeah, we're done with feature engineering. Do you have any more questions before I proceed? Alright. Okay, cool. So next is feature selection. So these are some of the basic filters that we can use. So the order of exclusions, it's up to you. So first set is per feature, per one feature. Check for business implementation. So first off is to see if this feature is available at implementation. So during model development process, you may have this feature at hand, but during the implementation, this feature is no longer used. So take it out. Next one, does this feature make business sense in the way that does it even okay? Does it even matter if you include a feature? Let's say the number of um, times that person went to the branch. Is that a good feature? Does it make business sense? Maybe not. So you can exclude it from your feature list. Second one is called concentration. So basically, if one value contains a high concentration of observations, then this variable may not provide much variability. So the behavior observed on the variable also may not be stable. So let's say that you have a tagging um, for whether the person has a mobile phone or not. And then obviously in today's age, you expect that maybe a lot has a mobile phone. So in your data set, it could be like 90% of your data. So if that is the case, there's really no point including it there because you expect like majority of the people to have it. The third one is on the signal. So we've discussed tons about this earlier. But if there's still a significant number of observations with null or missing values, except when it is a valid value to have, then exclude your data. Exclude your feature, sorry. Last one is on unique values. So it's applicable for categorical values with too many unique values. So let's say that this is like the name of your mobile device. So that could be a lot, and it also does not really give a good idea of the credit performance of the borrower. Okay, so in this case, you can take it out as well. The next set is on correlation and multicollinearity. So you can use pairwise correlation to determine if two variables are related. So if you still include both variables in your model, then it really does not give you new information. And then your results may not be reliable. And then multicollinearity basically It's kind of similar with correlation, but it's more on two or more variables. And you can check this out through the variance inflation factor or the VIF. Okay, so next is calculating for your information value. So we discussed this earlier, right? Here, where we talked about predictive power, right? So how do you actually calculate for your IV? It's actually pretty simple. It's just the summation of the percentage of goods minus percentage of bads times your WOE, which you calculate here. Now, the basic idea is that the higher IV, higher information value is generally better. And you choose features with an IV of greater than 0.1. But just to be safe, also, if your IV is greater than 0.5, then do further investigation. Otherwise, it could be like a confounding variable. Okay, so this one, the IV one, is on a, it's just on one iteration and it's on one feature. But here we have what are called proper methods. So basically, it uses what is called 3D search, and it looks through all possible combinations of features, and you benchmark it on evaluation criteria. So again, that's the difference. For here, here you're looking at one feature, but here you're also looking at its significance in relation to other features. So for example, well, there are three main ones. It's called backward selection, forward selection, and stepwise selection. So for the first one, is everyone aware actually of this? You're familiar? Oh, okay. So for backward selection, basically you start with an initial set of features and you gradually eliminate them one by one. Okay. And here we're using the p-value as the basis for eliminating your features. And then you stop when all the remaining features pass the selected significance level. Part of it, so you have backward selection. So you have also what's called the recursive feature elimination or RFE. It's kind of similar to backward elimination, but it uses feature importance. And there are actually packages where you use what is called check importance as the basis for eliminating variables. Okay. The forward selection part is actually just the opposite of backward selection. Basically, you start with one and then you keep adding one more until you have until you've added all the features that pass a selected significance level. Okay. And then from here, you also have what is called the recursive feature addition or RFA, which is just the opposite of RFE. Then lastly, you have stepwise selection. So stepwise selection, you can think of it as a combination of backward and forward. Please see the sequential forward floating selection or sequential backward floating selection to implement this one. And then last one in the note there are also other approaches for feature selection. So this one is called wrapper method. You can also try embedded method for your feature selection. Okay. So last, after feature engineering and selection, then you can run logistic regression if you're doing a conventional scorecard. Right. Basically, just get the binning, do the WOE transformation, and then you run a logistic regression using stepwise selection. You scale your coefficients based on the lower and upper bounds. And this is what you should come up with. This is what you call a scorecard, basically. Okay, so what it does is that it shows you the corresponding points per bin. So for example, for age, if you are with 32 years old, obviously you'll be given 20 points. And And then check for monthly income as well. Let's say you reside here, somewhere here, and that is an additional 10 points. And then for marital status, let's say you're single, so that's plus 7 points. And then you add it also to the intercept, which is 100 points. So it's pretty straightforward, actually, right? So this is an example of a scorecard. But this is usually the output if you run a stepwise logistic regression. But if you're using less conventional techniques, let's say you're doing XGB, like GPM, then you may not be able to create the same format, which you see on the left. So instead, we can use these tools to show how our features behave. Okay, so why is that such a big deal, actually? Because we are concerned also on explainability. This is because regulators may ask for features you used in the model. Okay, and again, this is usually in the case for other models models other than logistic. Okay, so on the left, you have what is called a B-swarm plot, and you can also use violin plot. It's mostly just the same results. Here's how you run it, and then it shows you this chart. Okay, how do you interpret this actually? So you can think of a SHAP value as like an additional contribution of the feature to the entire output. And here we see it just says impact on model output, right? Let's pick this one here, for example, H. Let's say that for this model, the higher the score, the better, right? So for SHAP value, you have a positive impact and a negative impact. And then here you can see feature value, wherein the blue colors means low value, and then the red colors means high value. Okay. So if you're looking at age, for example, what you can immediately notice is that the higher values reside on the positive side of your SHAP value, positive impact. So what this tells us is that mostly or in general, higher values for your age is a positive impact to your score. So it can give you higher score. Kind of like that. You can think of it that way. But okay, so but the B-smart plot on its own is in a general term, like meaning on the total population. So what if someone comes to you and says, "Hey, what happened to my score? It's so low now." So you can also use what is called a waterfall plot. And basically it explains the predictions per single observation. So if this one is just for the entire data set that you use for training data, you can do a deep dive per observation, and it looks something like this. So you have what is called like a expected prediction or mean prediction, which is here, for example. Oh, by the way, for this specific example, the X values here refer to log odds. Okay, so it can be different depending on your model. But let's say that the expected value is this this value here, but the actual calculated value for this specific observation is much lower. So what happened? Why am I getting a lower score? So then we can see here what really moved the score, right? And you can see that it's mostly because of the capital gain. So you can, sorry, will we be providing the slides? Okay, so we'll be providing the slides, right? So you can just take a look also here for more information on this. But basically, for this specific model, it's trying to predict the probability of earning, I don't have it here, of earning 50,000, I think, dollars. And then, so the capital gain currently of this specific observation is low. It's $2,000, for example. So because the capital gain is low, that resulted in this, uh, in a drop actually in the predicted output from the mean or the expected output. Is that clear so far? Sorry, clarifications on yes, please. Sorry, what?
How do you interpret in this first chart relationship and marital status?
Relationship and marital status.
First chart, yeah.
The next one.
How do you interpret that?
Okay. So the assumption here is that they probably did target encoding or W encoding early. Okay, let's go here. Sorry. You familiar? So okay, so they probably did some encoding at the very start. Okay, so for example, here, let's go back. Okay, my bad. So let's say relationship, right? 0. So it could be, okay, let's just focus on marital status. Maybe that's easier. So let's say marital status, 1 is single, 2 is divorced, something like that. 4 is married, something like that. Unfortunately, I don't have the data set. This is just an example, so I can't really say. Yes.
I was hoping how to interpret that.
How to interpret?
I was hoping. Then this one chart.
These one plot. Okay. Let's take a relationship, right?
I was hoping.
I was looking.
Hours per week. Oh, okay. Hours per week. Yeah, okay. So maybe a disclaimer for everyone. I don't have this data set. So I'm not really sure what each of these features mean. But we can say, let's say that this is hours per week at work. Something like that. So let's say that the more hours per week at work that you do, that would contribute positively to the score. So because you have higher value versus right here, right? The red ones would be high, and then the blue ones would be low value. Yes. Yes. Okay. All right. Wow, we're almost there. You guys still okay? Still alive? Okay, let's go to this one. This is performance metrics. Right. So typically for model development project, we monitor the AUC, the Gini, the KS, and you have what is called the confusion matrix. So I put that there as a note because usually credit risk scorecard development, the focus really is more on this because we want to check for risk ranking and major separation. But you can still use confusion matrix for, well, you can use it for deciding on a cutoff. Actually, is everyone familiar with the confusion matrix? Okay, cool. Yeah. So you can use the confusion matrix when you're thinking of like an automatic rejection. Which benchmark or which score will I do my automatic rejection? And that would be like I can optimize like a true positive rate or yeah, something like that. Okay, now take a look at this chart here. So the main objective really is, as apart from this metrics, is that you should also check for risk rank ordering or monotonicity. So what does that mean? So typically in a scorecard, you want to have higher score means better. Okay. Cool. So here, the bars here represent the bad rate. So what you want is for your bad rate to continuously decrease as the score increases, right? And the odds, on the other hand, okay, odds is just basically goods divided by bads. So what you want is for the odds to be monotonically increasing, right? The other thing that you may want to check is on PSI, which is basically a measure of stability of the distribution of your data. So this is also helpful if you're doing monitoring already. Okay, so for example, this is one data set, and then you also have the second data set. So you can just compute the PSI, and usually the benchmark for the PSI is 0.25. So if it's 0.25 above, then we're saying that there's a significant shift in your population already. If it's, let's say, 0.10 to 0.25, then there is moderate shift in your distribution, in which case it is highly recommended that you already monitor like your data. Okay. Oh, okay. So, right. So now we have what is called calibration and master scaling. Right, but before that, some terminologies. So we already know bad rate is the count of bads over the total count of the population. And then for odds, it's basically also known as good bad odds. And it's basically just the count of goods over the count of bads. Right. Let's go and discuss. So what do we mean by calibrating the score? So let's say you have two scorecards for two different products. So product A is this and product B is this. Can we say that the score of 400 is the same for both products? Something like this. All right. And obviously the answer is no. We can check for the odds ratio to validate this. So one product may have the odds of 2 for a score of 400 in product A, but the odds is 8 for product B. And so enters calibration and master scaling. So to do that is first we need to decide what is our master scale, and that needs to be decided by the financial institution or by your organization as well, right? What does it mean? So a master scale is the scale that all scorecards follow so that you are now aligned in terms of odds at each score. So to construct this, you need to set the parameters. So let's say that here's an example. The base score is 500. The odds at base score is 1:1, and the points to double odds is, let's say, 50. So what does that mean? So if we start with a score of 500, and the odds is 1:1. If we move plus 50 to the right, then your odds will double. So it's now 2. Add 50 again, then your odds double to 4. So it's just the opposite. If you subtract 50, then this will be halved. It's now 0.5. Okay. All right. So the next step is to, okay, so I'm gonna show master scaling in terms of the plots. So visually, just show you what it looks like. So first, from here, right? So you have the odds and then you have the score. You calculate the log odds, and then you plot the score with the log odds, like so. So this is now your master scale plot. And then from here, you can get this equation. So it's a simple linear equation, like also x plus b, right? And then if you go to your scorecard, so now you have a sample scorecard, right? And you have the bins, different bins. You also calculate the mean score and then the log odds of your own developed model, and you also plot it as like so, and you also calculate for the equation y equals mx plus b. Then you simply equate y1 equals y2, and you solve for x2. Oh, sorry. And once that's done, then so you see from here, it's basically just like shifting this line here to something that looks like this. So once we take the slope and intercept of both lines, you can get the calibrated score. And if you plot it, it should look similar to your target or to your master scale plot. I hope that's clear. Okay, last, I think. So this one is on score bands and strategies. Okay, so whatever you used as a technique for developing your scoring model, you should still be able to have several score bands that look like this, right? Okay, so so this is something that can be done. Let's say that you plotted, and these are the bins that you have. You plotted the cumulative bad versus the cumulative good. Okay, clear so far, right? Then you compute for the difference between your bad and then good. Then what you get is what we call the KS. Okay, the KS value, which is like the 17 point. Sorry. Oh, okay. So here the KS, the maximum separation is at 43.5, for example, here. So this can be used, for example, for getting like an initial like benchmark cutoff for separating for getting a automatic rejection. But again, it depends on what is the risk appetite of your organization. What I mean by that is if we employ specific cutoff, like automatic rejection for 600 from for score 600, meaning we only accept accounts with score greater than 600. So this is here. Then there's definitely a trade-off, right? That means that for example, for this one, you are automatically rejecting about, let's say, 70% of your bats. But at the same time, that means that you're sacrificing maybe 25% of your goods. Is that clear here in this chart? So the green one, right? Those would be your good accounts. So that is a trade-off if you employ this strategy. So this one takes also into consideration what does the business want? Okay, what are they willing to sacrifice in order to get a better portfolio? Okay, and then you can also, instead of just setting one cutoff, you can also specify the different risk bands. So very high risk, for example, would be the first two bands. High would be just these two, medium and then low. And then it will be different how you treat how you treat each account. So very high could be like automatic rejection. And then for high would be closely monitoring these accounts. So something like that you can employ as a strategy. Okay, so far, then I'll go to the next slide. So we've talked about a lot of things tonight. So now it's time to put them all together. So usually there are two main approaches, the conventional one and the non-conventional. Conventional would mean having an output of a scorecard that you saw earlier, which is basically just having a specific point mapped to a value. All right. So for data preparation, it could just be the same, right? You can handle same values, outliers, extremes, etc. For feature engineering, So the conventional approach usually uses classing, the one that you see where we do some binning, check for monotonicity, check for the population percentage per bin, and then applying WOE encoder. After that, the feature selection is basically correlation multicollinearity, checking for the IV, and doing stepwise selection for using logistic regression, right? And then for explainability, that will be the scorecard itself, where you see the value and the corresponding point. The non-conventional approach could be the same data preparation step, but then you might use, I don't know, maybe target encoding instead of the usual, or you can still use WOE if that is something that you want to explore. You can use correlation with the community still. So this one is another wrapper method that you can also take into consideration. You can use RFP or RFA as well. And then in terms of the model, you can use XGBoost and do hyperparameter tuning. You can also try like GPM, and actually in other you can also try survival analysis, but that mostly would be for BD models. And for explainability, since we may not be able to do it the same format as logistic, then you can just take a look at SHAP or feature importance to explain your features. Okay, and this is an example pipeline, a simple pipeline that you can do in Kubeflow so that you can just run it whenever you want to develop a new model or a different product. That's it. Okay. I need water. Okay, guys. Are there questions? Yes, please. Good drink.
Okay, so the question was, what are the tools on stages for online people?
For stages?
The tools.
Stages. I'm not clear. What? Oh, okay. So actually, they're all in Python, actually. So yes. So if you go back to here, these are some packages, modules that you can use. Depends on what. Sorry, wait a version here. You can use some of this if you want. I think this one on itself, on its own, would be another session. Feature engineering itself is another session. But yes, all of these are done in Python. Okay. Other questions that you may have? Yes. Yes. Sorry. I am deaf.
Thank you. I just have one question on model selection, because one of the myth that I often heard on about credit modeling is that people tend to use those traditional methods like logistic regression because of higher explainability
Yes.
as compared to like XGBoost or like even some deep learning methods. So just wonder, like, is it still the practice that you still prefer those logistic regression, or like is there any implementation on, like, for instance, deep learning models
Okay.
for credit modeling?
I was waiting for that. Thank you, Berlin. Okay, yeah, so yeah, this is actually a common question or concern from credit risk. And yeah, so it depends. It's a function of the comfort of of the management and also the regulators. So I'm not sure how it is for Singapore, for example, but right now, just to give you an idea, when I started with credit risk, we are leaning towards traditional logistic regression. That's the answer to everything. But more and more banks are opening up to using right now XGBoost and maybe other tree-based models, tree-based approaches. For deep learning, that is still something not sure if there are definitely researches on that. There are papers wherein you use ANN, for example, to come up with a credit risk model. But for now, what I can say is at least this one, tree-based approaches would be you can use at least. But it depends on the regulator.
I think in general, tree-based models on tabular data outperform a lot of the deep learning models too. So I think that's why it's sort of the de facto now for a lot of the tabular data, which is pretty much like these credit risk models. So, and they have the built-in explainability, which you wouldn't get with a deep,
Yeah.
So,
Yeah.
Yeah.
Although for neural nets, I think that you can still use some explainability tools. Maybe there's application of chat in neural net, but it's still not like there's still some hesitation towards using it. But I would say though that you can always argue with if you can show like the business strategy, if there's a big improvement in the business strategy, for example, and the performance is a huge uplift, then it's definitely something to consider and to explore. More questions?
Why didn't you at least enough to go back?
Yeah. Okay. The regulators would check. Okay, so the question is, why would it depend on the regulators if it's something internal to the bank? So banks are subject to regulators, right? But if your credit risk model is something that will not be reviewed by them, and it's just within your organization, then definitely you can explore other techniques. Yes, so definitely explainability is like one of the main concerns. So it's important to identify what are your top features and then how your feature values affect the overall scores. Yeah. Yes, one thing.
To produce a linear trend of odds.
To produce a linear trend of odds. For binning, yes, you can apply other approaches as well. Although I haven't really tried that. So mostly when we do classing, it's mostly manual. So therefore we just tend to rely on other encoding techniques. Let's see. Other questions? There are no more questions?
Yeah, I mean, if there are no other questions, yeah, thank you all for coming. It would be great if we can have a brief intro of people who have joined us here. Yeah, so, oh yeah, sorry. Yeah, the people on joining us online, thank you so much for joining. Hoping to see you forward in more of such events. And yeah, also you guys also please contribute and would be love to have you in the office sometime. And yeah, thank you so much for joining. Yeah, so for